Okay, our next speaker is Teagan Blaikie from Southern Geoscience. She'll be talking on geophysics for mineral exploration. A bit of background on Teagan. Holds a PhD in potential field geophysics and an undergraduate specialisation in geology and geophysics. She is a specialist in qualitative and quantitative interpretation of magnetic and gravity data, with over 10 years working in academia and government, including CSIRO and NTGS. She has experience in Proterozoic basins of Northern Australia, poly-deformed terranes, sediment-hosted mineral systems, and structural geology and mapping. Please welcome Teagan.
Thanks, Donna, for that introduction. Good morning, everyone, and good morning to everyone online who's joined in. What I'm going to go through today is just a bit of a introduction to geophysics for mineral exploration. All right, so we'll go through a little bit about the role of geophysics in mineral exploration, touch on a couple of different geophysical techniques. So just some brief introduction to a few techniques that I'm assuming most people in the room are geologists, so probably the techniques that would be most intuitive for you to look at, interpret, and that you're probably more likely to come across on a sort of day-to-day basis. And then we'll touch on the scales of interpretation for exploration, and I've got a case study using magnetics at the end of this presentation. So, sorry for the people online who might not be able to see me. I can't see the slides well there. Can everyone still hear me okay? So geophysical techniques, they're really crucial for mineral exploration and mineral resource delineation. And particularly in Australia, which is under a lot of cover. As we try and work more and more undercover, geophysics is really essential to our exploration programs. The advantage of geophysics, it's a non-invasive tool. A lot of the techniques are airborne. We can rapidly collect a lot of data. And we can use this data to try and test hypotheses about different components of your mineral system. And that's from that province, the really large scale, working down to your district, to your project, down to your prospect scale. But to improve the chance of success in exploration, you need to know which techniques to use, when to use them, and at what scale they're suited. They're best suited to. So what I've got an example here is an example of 6 tier 1 deposits looking at the magnetic data. And if you look at where those arrows are pointed in each of those images, you'll see that they're probably in unusual points of the image. They're maybe not where your eye is drawn to straight away. Each of these deposits is not a standout magnetic anomaly on its own, but there are clues in the magnetics that can lead you to where you might have mineralization. So in the interest of time, we won't go through all of these, but if we have a look at maybe Tom Price looking at the iron ore, this is the Turner syncline in WA. You can see you've got a very strong magnetic anomaly through there, and where the deposit is, you can see you've just got a reduction in the intensity of the magnetic response there. So that's an area where you've had potentially some alteration. You've had some alteration of your magnetite in deposit to the hematite. It's less magnetic. You're seeing that in the magnetics there. But if you were just to look at that, your eye is probably drawn to where the highs are, the most intense part of that image. So just important to keep that in mind, that the geophysics will help you lead you to where you might have mineralization, but you may not be able to see it directly. And it's also not about big anomalies, it's about that context that you get from the geophysics. So what I have here is a bit of a recipe for decision making in exploration, how you might best use geophysics. And it sounds pretty intuitive, but as a consultant, I come across a lot of clients who want to look at their tenement. They haven't really considered the regional context or the regional context of their data. So really important to do your regional scale evaluation. Have a look at the geophysics and your other geological data as well. test your geological concepts, work out where your major structures are, your 3D geometry, your structural architecture, and from that, select your area of interest for further exploration. Then move down to your district or your project scale evaluation. This is where you want to start refining your regional scale interpretations, constrain your structure, constrain your lithology, start answering questions about potential styles of mineralization at this scale, and determine your targets that justify exploration at the prospect scale. And then when you get down to this target scale, it's when you want to maybe start thinking about designing a drilling program. And this is where you might start to apply further geophysical surveys. You want to try and test those structural, those lithological controls, determine if you've got any potential alteration that may lead you to where the mineralization is. You really want to narrow that uncertainty associated with drilling by applying the right geophysical technique at that scale. And at every one of these scales of evaluation, sort of consider what data you have, what you might need in the next step. So maybe you want to infill with high resolution magnetics or fly airborne EM surveys, things like that. So you need to think about what the next step is, what data you might need next. So touching on geophysical methods, there's a lot of different techniques. You've got potential fields, magnetics, gravity. You're probably going to, as geologists, come across those two data sets quite a lot. You've got your EM methods that can be acquired on the ground, airborne, or downhole. A whole lot of electrical methods, seismic, and then other methods as well, like your remote sensing methods, radiometrics, satellite, multi-hyperspectral data that you can all use. So many different methods. So you need to think about which do you want to use, what's right at the right scale. So a good way to start thinking about this is start thinking about the physical properties of the system that you're working in. Petrophysical properties, they are that link between the geology and the geophysics. So if you're targeting a particular mineralization style, the physical properties of those host rocks, areas of alteration and potential mineralization, you need to think about that, and you need to think about what geophysical technique is going to detect that. So what do I mean by that? Well, here I've got an example from a low sulfidation epithermal deposit. So this is from Waihi, an example from the Waihi district in New Zealand. And in that column on the left, you've got the physical characteristics of the rocks, things like magnetite destruction, clays, alteration, structures, intrusives, things you might need, or the ingredients that you need to form mineralization. The middle column is the petrophysical characteristic of the physical characteristic. So magnetite destruction, you're going to have no magnetization. So those are the physical characteristics. So you want to start thinking about what are your mappable criteria? How is that expressed in petrophysics? And then what is the geophysical method needed to actually detect that? So we have that in the right-hand column. And the boxes highlighted in red are the characteristics that respond to, say, magnetics. So I have an example here from the Waihi district in New Zealand. And if we just go back to this slide here, some of the characteristics we're looking for, magnetite destruction, say major structures. Let's have a look at that in the magnetics. You can see we've got the reduced to a polar data on the left and the derivative on the right. You can see you've got these very magnetic areas defined by these sort of red, yellow responses in the image there. On the right, you can see that sort of really high frequency response. So they are volcanic rocks. They're very, very magnetic. And then you've got these hydrothermally altered zones causing this really kind of flat, bland-looking response in the magnetics. And these are zones associated with hydrothermal alteration, which has caused magnetite destruction. So looking at an image like that starts to get you into the ballpark of where you might be getting a mineral deposit forming. And you've got the Waihi gold mine, sort of roughly where this red arrow is pointed, right there. So looking at that kind of large scale at the geophysics, or signs of essentially alteration can start to get you into sort of that area where you want to be working. So next up, very briefly going through a bit of an introduction to a couple of geophysical methods. And as I said earlier on, these are the methods that you're probably more likely to come across and use to sort of day-to-day. So there are a lot more methods that we can go through. We don't really have time to do today. These ones quite a lot. So,
Teagan, we've lost the microphone.
sorry. Is that better? Yeah. Maybe I'll keep going and then. So, touching on gravity, as I mentioned earlier on, petrophysics. Thank you. Can you hear me now? Yeah, yep, there we go. Petrophysics are that link between the geology and the geophysics. So for gravity, that is density. So I've got a chart up on the right of the common densities that you would see expressed for different rock types. So things like regolith, very low density, sediments, again, generally pretty low. Start getting into your metasediments, your metamorphic rocks, they'll increase in density, and then sort of your felsics and your ultramafics are going to be denser again. So it's important to think about what type of rocks you might have in your system, how they might be expressed in the data. So it started with gravity because it's really quite simple to understand. If you have a rock body with, say, a density contrast, this example's positive, that could be negative. But if you've got that density contrast with surrounding rocks, you will have an anomaly, and that anomaly will be located over your density contrast. So the size, the amplitude of your anomaly, that's going to be proportional to the size of your density contrast. If you have high contrast, you're going to have a larger anomaly. If you've got a larger volume, again, you'll have a larger anomaly. But it is relative to depth. So as that rock body gets pushed deeper, your anomaly is going to get a little bit broader, a little bit flatter. That's kind of the gist of gravity, pretty kind of simple technique to understand. So when you're looking at an image, a few things to remember are your highs and the lows that you're looking at. They're going to reflect density contrasts. The gravity anomalies, the shapes pretty closely resemble the shape of your geological body, and your signatures are additive. So if you've got regolith, that signature from that particular layer is going to add on to the signature that you're getting from the basement. So you're seeing a bit of a mix of signals in there. If you're getting broad variations in your response, usually relates to features that are deeper, whereas if you're getting quite small anomalies, they're going to be close to the surface. Gravity, great technique, can be used at all scales, right from the regional, right down to the prospect, even mine scale. Good data set to use. And we can use it for a whole range of things, looking at regolith, lithology, structure, and occasionally we can use it to directly detect ore bodies. So on the right-hand side, there's an example from the Carapatina IOCG deposit. Got a nice bullseye gravity anomaly directly coincident with mineralization there. So touching on magnetics, so that property that we're measuring with magnetics is magnetic susceptibility. Magnetic susceptibility can be a lot more variable than, say, density over a range of rock types. Generally, sedimentary rocks susceptibility will be relatively low, with the exception being banded iron formations, which is really quite high. Otherwise, it can be somewhat variable depending on your metamorphic rocks, what the protolith of that was, and igneous rocks. Really depends how much iron you've got in that particular rock type, how magnetic it will be. It's not something that's necessarily, magnetic susceptibility is not diagnostic of rock type, but important to sort of understand that range when you're looking at the magnetic data when you're trying to interpret lithology. So how does magnetics work? Well, hopefully you'll know the Earth has a magnetic field. It's generated by the outer core rotating around the inner core of the Earth. The magnetic field comes out of the Earth at the poles, and then rotates around and goes back in at the north. So if we have a look at this, this is basically what we're measuring during a magnetic survey. So we'll have a plane that'll be flying over a particular area, and it's measuring changes in the strength of the Earth's magnetic field. So if you've got a magnetic mineral or magnetic rock type in the subsurface, the Earth's magnetic field is going to induce a response in that, and then that strengthens the field at this particular point. So here we've got a magnetic source body, and you can see where these field lines that from the induced component from the Earth's magnetic field, where they add up, you get an anomaly over that point. And then you'll see this is an example from the southern hemisphere. It's slightly offset from our source body due to the inclination of the field, and there's quite dipolar response there. So there's some few sort of processing steps that we apply to reduce that back to what it would look like if the field was vertical. We get nice symmetrical anomalies. Makes it a little bit easier to interpret. But very briefly, that's how magnetics work. We're basically measuring how magnetic the rocks are beneath our feet. And we've got an example from the aeromagnetic grid of the Australian continent on the right-hand side. You can see how much detail you've got in that. So really, we're just measuring tiny amounts, mainly magnetite and pyrrhotite. That's kind of what we're measuring from our magnetometers. And we can see that down to about depths of tens of kilometres. So generally, magnetics is a really excellent mapping tool, and we can use that right from that regional scale down to the prospect scale. And if you're working in Australia, a lot of this data is free to download. So if you don't have data for your project area, jump online tonight and download it. Very easy to download, look at, use, and sort of integrate with the work you're doing on a day-to-day basis. We saw this example earlier from the Tom Bryce district in the Turners Incline. So this is where we're basically getting alteration of massive magnetite bits that's been altered to hematite, causing a reduction in the magnetic intensity due to that destruction of magnetite there. So touching on EM, so the properties that we're measuring there are conductivity and resistive, so how well the Earth conducts or resists the flow of electricity. You see you've got things like massive sulfides, graphite, even saline water tend to be quite conductive, and that's really important for our EM data. So how does EM work? Well, you'll have a setup like is shown in the top right there. You'll have a transmitter and a receiver loop there. You'll run a current through the transmitter loop that will induce a magnetic field that generates basically secondary currents and a secondary magnetic field in the Earth, which is then measured by the receiver. And you can vary the properties of that transmitter and that receiver to basically investigate different depths. And we can collect the data airborne. Tends to be rapid, quite low cost coverage. Will give you less penetration down compared to, say, a surface EM method. And then we can also collect data down holes, basically to as deep as we can drill. So if you've got massive sulfides, EM is the dominant and sort of the first choice method that you would use to try and detect that. It can also be very useful in mapping conductive materials. So if you've got gold in conductive shear zones or sediments, conductive regolith, channel line deposits, paleochannels, lithologies, EM is good for that. Ground EM will give you better depth penetration than, say, an airborne system, predominantly just because of the high power of that system. And if you've got downhole EM that can see undercover, you can get improved resolution at depth, and is also helpful to understand your ore bodies. So a couple of examples on the right. So you can see an example from Paleochannel there. An example from Geoscience Australia, they've flown airborne EM at 20-kilometre line spacing across not quite the whole continent, but it's getting there. And that's sort of a really good data set to have a look at. If you're not sure if, for example, if EM is going to work in your area, it's probably a couple of lines in the region or nearby. Download that, have a look at it, see what kind of response you're getting. If it's a technique that's going to work or not. So that's a sort of pretty good data set just to get a feel for how well EM might work in a particular area. Just got an example of a deposit discovered using EM here. So this is Emily Ann. It's a typical komatiite deposit. It's located at a depth of about 200 metres, quite shallow dip, and it's surrounded by quite resistive host rocks. The deposit itself has been structurally remobilised from an ultramorphic contact. So if we look at that image in the top left, that's the magnetics, and you can see where the deposit's been outlined. Outlined there, you'll see that it's offset a little bit from the magnetic anomaly. So in this case, the magnetics was really good for getting in the ballpark of where the deposit was, understanding the structure, understanding lithology, and then that was followed up with some EM. Lots of different conductors were identified here. Most of them were probably sulfidic sediments. But if you have a look at this profile shown on the bottom right, over the deposit itself, you're seeing you're getting quite a conductive anomaly where you get those massive sulfides. Radiometrics. So radiometrics that will measure the gamma radiation emitted during the decay of your naturally occurring radioactive elements, so things like potassium, thorium, uranium. It's a surface detection technique. So it's really looking at that top, say, 20 to 30 centimetres of the Earth. That's sort of what we're detecting. So if you've got lots of cover overlying your basement, you're not going to see that signal in your radiometrics. You're just going to see the signal of the cover there. But where your geology is exposed, it's otherwise a really good mapping tool. So usually you display your data as images of potassium, uranium, or thorium, or you can combine them to make a ternary image like we've got shown on the right there. You can see that's an example from the Hamersley Basin in WA. You can see sort of some beautifully folded stratigraphy of the basin there. So really great mapping tool when your geology is exposed. And finally, just touching briefly on hyperspectral and multispectral data. So I think there's another spectral talk after this, so I won't go through it in too much detail. But basically, we're looking at so some images. They can be airborne, they can be collected from a satellite. You're recording data across a wide range of spectral bands, covering different parts of the electromagnetic spectrum. And they correlate to different wavelengths that may represent, say, different minerals, vegetation, water. So you can look at that imagery. A lot of it's free to, so using Sentinel or Aster data, a lot of it's free to download and have a look at. And again, a really good mapping tool if you've got outcropping geology or you want to characterise the regolith. Just a good data set to have in your suite of data that you're using in exploration. So there's many methods that we can use, and these are often applied at different scales depending on the purpose of the survey. The cost for collecting your different data sets is going to vary at different scales. Often you'll have, typically in Australia, you'll have regional scale gravity, aeromagnetics, and we're getting to that point where we're getting regional airborne EM. As well. So that is data that has been flown by Geoscience Australia and the various geological surveys that is freely available to you to access, download, and use in your exploration. When you get down to that prospect scale, you might be looking to consider infilling that with higher resolution data or using a different technique, depending on what you're looking for. So as you step down in scale, then your cost for acquiring data goes up, but generally less than it would cost to drill a hole. So good to do a bit of geophysics, reduce that uncertainty of where you might be drilling. So just sort of touching on this concept of scales of geophysics for exploration again. Starting at the regional scale, this is where we want to start thinking about evaluating regional data sets, selecting your area of interest for further exploration. Then you want to step down next to your district, to your project scale, refine and constrain the interpretations that you did at the large scale, refine those, work out your targets that are going to justify exploration at the prospect scale. And at the target scale, you want to narrow that uncertainty associated with the drilling. So you want to apply different geophysical techniques that are going to help support where you'd like to drill. So I've got an example coming up. So this is from Menzies sort of Comet Vale, Gungari Gold districts in the Kalgoorlie region. It's a world-class gold and nickel province. There's less than 5% outcrop here, quite a lot of cover. So geophysics is really the key driver for exploration out here, and aeromagnetics been really key for that. So there's quite good, excellent quality, quite extensive aeromagnetic data available out here. There's also pretty good mapping, so there's not a lot of outcrop, but what outcrop there is very well mapped, and that's sort of good to integrate into our interpretation of magnetics as well. And the challenge out here is to try and identify new exploration targets undercover. So thinking back to our sort of conceptual program for trying to work through your data sets, start from the regional scale, have a look at the data sets that you can access for free, have a look at things like gravity in your area, have a look at the magnetics, radiometrics. Remember, we're only imaging the top 20 centimetres here, so if you've got a lot of cover, it may not be particularly helpful. In this example, you can see that there are some trends if you compare that to the magnetics, where you're getting those sort of linear magnetic highs. You can see there are some trends in the radiometrics there. So that can help you with your mapping and your interpretations of other geophysical data sets as well. And you put those together with the available mapping data, you can come up with a bit of a regional interpretation. Look at where your major greenstone belts are, where your major shear zones are, plot up the locations of known mineral occurrences, work out where you might want to look, where you might want to step down in scale and focus your exploration. So we're going to zoom in on that yellow box in the next few slides into our study area and look at some data there in a bit more detail. So I've selected that as our project area. And at this stage, we want to start to refine and constrain our structural and our lithostratigraphic interpretations. We want to better understand the mineral system, where you might want to target exploration at the next scale. And now we want to interpret basically local scale data. So if you've got magnetics, gravity, radiometrics, any other data sets you can get your hand on, integrate that with the available geology. And at the same time, be thinking about if you want to infill any areas with some high resolution data. So having a look at that, this area in a bit more detail, you can see that's got the 1 to 100K map on the left there. Lots of cover, but where you do have outcrop, gives you some good information. You can see you've got some outcropping greenstones, a bit of granite there, a few mineral occurrences, which sort of be key to when you get to the targeting stage to consider. And you've got some really good magnetics on the right-hand side. So that's 200-metre magnetic data, acquired in the 1980s and is now open file data. So we can put those two data sets together. If you have a look at your mapping and your magnetics, we might have multiple images of the magnetics with different processing applied to really enhance how we interpret it. This is just a grayscale derivative image here. We can make some observations from the magnetics based on that. integrate that with the map geology, and we can come up with a working solid geology interpretation. And from that, we can start to define what our exploration targets would be at this scale. So here looking at some shear zones where you might have flexures in those shear zones, lithological contrasts, trying to really understand where do you want to focus your exploration at that sort of next project scale. So next we're going to zoom in onto that box on the right there. And say that that interpretation there was at that 1 to 250,000 scale. We can push that a little bit further. So here we're looking at the data at that 1 to 100,000 scale. Zoom in on the map, you can see there's a lot more detail that you can observe in the map at this scale. A lot more detail you can get out of the magnetics. Again, we can put them together, interpret that, really refine the interpretations that you've done from the larger scale, keep building it up as you zoom in. And then we can refine our exploration targets. So you can see the dashed lines on that map on the right shows what we had at the regional scale. We can really narrow down on the areas that we want to look at that next scale. And that's when you maybe want to start to think about designing a drilling program. So you want to apply a geophysical survey to try and test some of your ideas about your mineral system. Things like structural, lithological controls, identifying any alteration. You really want to narrow that uncertainty associated with drilling with further geophysics. So what would you do next here? Maybe you get higher resolution magnetics. That was done in this area. You can see the amount of extra detail that is enhanced from flying that higher resolution survey there. Maybe you want to zoom in on some of those targets, do some quantitative analysis, try and do some modelling and inversion, just constrain the depth, the dip, the geometry of some key anomalies. If you're looking for things like massive sulfides, you might want to consider EM. If you've got perhaps more disseminated sulfides, perhaps do IP or resistivity survey, depth of cover, a few techniques you can try, size, for example. So lots of different techniques that you can do next to really help aid in your decision of where you want to put a drill hole. And so geophysics should be used to support that.
To summarise, geophysics can be useful in all stages of exploration, but you need to understand what you are targeting and choose the right geophysical tools to do so. Geophysics can only sometimes directly detect a target, but the data often tells us critical clues about the geology. So it's really important to consider what you are exploring for and what the key properties of a particular style of mineralisation and their alteration systems could be. Understanding this will help you decide on a method that will be most effective. This could be derived using petrophysics, either downhole or from samples or core, or even just a general understanding of the rock properties. We also want to sequentially focus exploration and analysis of geophysical data from the regional towards the prospect scale, and use geophysics at each scale to constrain and answer questions about the potential for different styles of mineralisation. And finally, remember to integrate the geophysics with any geological data you have to get the most out of the data and an interpretation of it. Thank you for listening to this presentation. If you want any more information, then feel free to email me. We also offer 2-day workshops on the integration of geology and geophysics for both aeromagnetic and AEM interpretation. Scan the QR code on the left if you want more information on these workshops. Thank you.